Good day, Dr. Rael and Dr. Norhayo. I'm Eddy. Today is my great pleasure to present you on my final year project, which entitled Performance Benchmarking of Full-Scale Acid Gas Removal Unit. Before we proceed to the details of this project, allow me to introduce you what exactly is acid gas removal unit, also known as AGRU. So this is the flow diagram of the AGRU. Firstly, we have the natural gas coming from the upstream and it's going to be fed inside this absorber. So what's happening inside this absorber is that under the high pressure and also the low temperature, with the help of the solvent with a composition of 50 weight percentage of the DIPA, diisopropanoamine, 25% of the water, and 25% of the sulfurlant, it's going to treat this natural gas by removing the CO2 and also the H2S. So this treated gas will have the CO2 of less than 50 ppm and H2S less than 3 ppm. So from this bottom of the absorber, which is known as the rich amine, is going to travel and flow into this regenerator. Inside this regenerator, the solvent is going to be regenerated, and it is known as the lean solvent, which is going to recycle back to this absorber. Whereas the CO2 and also the H2S, which are stripped from this solvent, is going to be travel to the incinerator as a sour gas. So for this project, there are two main focuses, which are the focus one would be the reboiler duty, which will look into the steam consumption, and the focus two would be the lean solvent circulation flow. Next, I present you the problem statement for my project today. There are a total of two problem statements that I would like to mention. So for the first one would be the current benchmarking of AGRU that's provided by company A is actually very poor. So there's a need to suggest an alternative benchmark methodology in order to optimize and also better control the AGRU. And next, in terms of the optimization of AGRU, there are two main parameters, which are the circulation flow and also the steam flow. In terms of the reboiler and also the preheater are essential because it leads to money saving. Now, let us look into the objective and also the scope of studies of this project. In terms of the objective, we have three main objectives that I would like to show you. So firstly, we are going to analyze the current benchmarking system, and I'm going to determine if it is suitable for the current operation of AGRU. And following next would be the new benchmarking approach system development via the MLR models. And next, I will build an ideal benchmarking system using the steady-state simulation via the software called ICON and assess the current operation status. In terms of this scope of studies, there are four scopes of study that I would like to show you. Firstly, which is the analysis of the current operation condition and also the current benchmark provided by company A. And next, which is the MLR model development, and followed by the steady-state simulation ICON study. And finally, I will study on the effects of change of CO2 composition, for which the targeted studies are the amine circulation flow rates, the reboiler duty, and to ensure that the treated gas composition does not violate the operations of this LNG plant. So after understanding what are the objective and also the scope of study, right now let us proceed to a little bit on the literature review summary, for which I'm going to talk a little bit about the optimization approaches that have been taken by the industry and also by the researchers' studies. So for the optimization approaches, I have separated into two parts. Firstly, the industrial approaches and followed by the scientific journal. In terms of these industrial approaches, firstly, I have the RTO, the real-time optimizer. RTO is basically a closed-loop mechanism that started with the mass energy balances and ended with the optimization advisory. So in short, this RTO is able to provide optimization advice to the operators or to the engineers so that they can optimize their plant just in time. And next, I have the MAP, the Molecule Allocation Program, which is ventured into by Malaysia LNG Senjam Berhad, MLNG. So what this MAP does is that right now, imagine that you have a plant and there are three trains. So these three trains, they have different PTE, the plant thermal efficiency. So this MAP is able to determine that train 2 has the highest efficiency and the lowest will be train 1. So by using this MAP, we are able to feed in more molecules of the natural gas into train 2 and then reduce the feed into the train 1 so that we can actually optimize and improve the overall production. And next, which is the solvent selection. So basically this solvent selection, it is one of the approaches that's taken before we actually construct the plant or before we do the literature study. And we have the primary amine, secondary amine, and also the tertiary amine. And here are the pros and cons for the solvent selections of primary, secondary, and also the tertiary amine. And moving on next, let me look into the scientific journal. So for this scientific journal, we look into the parameter analysis study, and there are steady state and also the dynamic state. And it is determined that lean solvent circulation flow, reboiler steam flow, lean amine temperature, and also the energy traffic in the absorber are the essential parameters that can contribute to a lot optimization and money savings in AGRU. And lastly, we have the control of the optimization, in which control is believed to able to reduce the cost because it takes into the transient study into consideration and also the valve actions into considerations in order to optimize the overall process of AGRU. Moving on next, allow me to present you what are the methodologies that I have used in completing this project. So this is my project workflow, for which I started with the data gathering and the parameters identifications, and followed by the statistical data analysis on the current benchmark system against the current operational data. So at this section, I had determined whether the current benchmark system provided by company A is valid or not. And next, I venture into the very first new benchmark system, which I call it as the MLR model. It's the multiple linear regression model via the Excel-based. And next, after this MLR model, I ventured into the approach 2, for which I developed icon steady-state AGRU models, and this model is used to determine the required circulation flow, steam flow consumption for the reboiler and the preheater at different CO2 feed gas content. So after that, I compared between the current benchmark, approach 1 benchmark, and approach 2 benchmark, and determined the pros and cons for the AGRU optimization. Moving on next, like I've mentioned, for the approach 1 will be the multiple linear regression model development. So in order to develop this model, I have split it into 4 phases. For the phase 1 will be the data collection and abstractions, followed by the data conditioning, modeling, and also the validations. For phase 1, which is the data collection and abstraction, basically I collected and extracted the important data that I obtained from company A. In terms of the phase 2, I conditioned the data by eliminating the bad data that's not suitable for the model development, and I segregated my data into 2 parts. Firstly would be for the modeling, and another set will be for the validations. For the phase 3 modeling, I developed my model using the Excel-based, and I simplified my model by observing the adjusted R-square, p-test analysis, and remove the outliers. Eventually, I have to validate my model by using the validation set that I've segregated just now, and I'm going to observe my adjusted R-square and p-test and also the collinearity by using the variance inflation factor, and this is the final form of my model. Next, here I present you my approach 2. So basically for this approach 2, I developed this model by using the icon simulation software, which is in steady state. So basically this is my model. Here's the absorber, here's the regeneration, this is the lean solvent circulation line, and here is the reboiler. So to build my model, here are the data that I've used. This is the process design basis for the statistic model. Here is my amine details and the details for the absorber, and lastly the details for the regeneration column. Next, I have the current benchmarking system from company A, and these are the data that I've used to build my icon model base case. Without further ado, let us move into the first part of the result and discussion, assessment of history data-based benchmark. Firstly, let us look into the lean solvent circulation flow. So here I present you the graph of the lean solvent circulation flow in year 2018 operation of company A. So the dark blue, it represents the current actual flow, whereas the white dots here represent the current benchmark. So just by looking at this graph, it can be seen that, well, the current benchmark is actually fitting well with the actual flow. Let us look into more detail of ANOVA analysis. Based on the ANOVA analysis, the average flow of this operation is around 11.91, whereas the current benchmark 11.46 kiloton per day, which means that the operation is operating higher than the current benchmark. Since right now we are dealing with optimization issue, we have to understand a little bit theoretical parameters relationship. Here I present you the relationship between the circulation flow, reboiler duty, and also the feed flow. According to study, the lean solvent circulation flow is actually having a linear relationship with the reboiler and also the feed flow. Right now, let us shift back into this graph. We can see that yes, the current benchmark is having a linear relationship, but there are few spikes here which is not consistent. This is a spike 1, spike 2, and also the spike 3. Well, you might say that this is just a spike, it doesn't really matter. Well, make no mistake, it does matter, which leads to the first mistake of my analysis today. So for the mistake 1 that I have determined from this current benchmark would be 1 meter cube per hour of this solvent can actually lead to an increment of the reboiler duty of 151.91 kilowatt, which means that your steam flow will increase and your operation cost will increase at the same time. And of course, this is not the only mistake that I determined from this. Secondly, from here, you can see that for each of this production capacity, there's only 1 point data. It means that this data, it does not consider any CO2 composition variation, which is incorrect because in an actual LNG plant, the CO2 variation, it varies all the time. It is fluctuating. So without considering these fluctuations, this benchmark will left questionable. And in terms of the next mistake, which is the mistake 3, which is about the boundary set of the AGRU, let us proceed to the next slide. Right now, let us look into how an LNG plant actually looks like. So basically, these are the flow of an LNG plant. We have AGRU, dehydration unit, mercury removal unit, liquefaction, and we produce our LNG. So for the current benchmark, the boundary set is actually at all of this region. It means that it's from the beginning till the end. But is it valid because we are just looking at AGRU? My answer would be no. Instead, what it should do would be the boundary set, it should be at the AGRU. This is because if let's say we are setting at this whole region, there are a lot of process difficulties that could happen in between. And it means that our benchmark, if let's say we are going for the whole, it will be inaccurate. So instead, we should just focusing on the AGRU boundary set only. Next, let us look into the reboiler stream flow. So here is the graph for the reboiler stream flow, and through ANOVA analysis, it is determined that in terms of the operation, averagely it is operating lesser than the current benchmark, for which the operation is 2.11 kiloton per day and current benchmark around 2.19 kiloton per day, which is approximately the same. So let us look into the trending of this current benchmark. It is rather scattered and it is not in the linear relationship, which brings me to the mistake 1 of this graph. The general trend is messy and it is not in linear. Earlier, I've mentioned that the reboiler stream flow has a linear relationship with the circulation flow. So right now, why don't we make a comparison? So here I pulled out the lean solvent circulation flow, and it is determined that there is a mistake too, for which the reboiler steam flow, it contradicts with the circulation flow. How so? Let us see. This is the first point for which there is a decrease in the steam flow, but the circulation flow increases. Not only this point, here also the same thing, decrease in the steam flow, but there's an increase in the circulation flow. And the last point would be also the same, there's a decrease in the steam flow and there's an increase in the circulation flow. So from here, what we can conclude is that this reboiler steam flow benchmark is actually contradicting with this lean solvent circulation flow, which means that both of this benchmark, it's inaccurate and left questionable. Moving on next, let's proceed to the results and discussions of the multiple linear regression models. Prior to the MLR model, I've done a little bit of the data analysis on the feed gas CO2 variations and also the feed flow rate variation. In terms of the CO2 variation, it is basically between 2.34 mole percent and with a maximum of 7.49 mole percent with the average of 5.47 mole percent. In terms of the feed flow rate, the minimum will be around 7.1 kiloton per day with a maximum of 11.78 kiloton per day. Now, let us look at the reboiler steam flow performance study. So here is the loading plot of the principal components for the reboiler steam flow by understanding the relationship between the reboiler steam flow and also the 13 variables here. So after developing these MLR models, here is the results and with a final equation which consists of 4 main variables only, x2, x5, x6, and x7. And it is determined that the adjusted R-square is approximately 0.89 and the p-value is actually 0, which means that it is less than 0.05, which shows a high significance on these variables towards this reboiler steam flow. And not only that, in terms of the VIF, the variance inflation factor, it is less than 5, which means that the variables that selected here, there are no collinearities or redundancies. Right now, why don't we do a little bit on the process analysis based on this equation? So firstly, we can see that our S2, it has a positive variable. Whether it is valid? Yes, it is, because when your feed gas CO2 content increases, it means that you require more solvent. More solvent means you require higher steam flow for the regeneration process. So let us see to the second variable, which is X5. In terms of the feed gas flow, when your feed gas flow increases, meaning your reboiler steam flow increases as well, it means it is valid because more feed gas flow means more steam flow. And next, we have the X6, the flash gas pressure. We know that our regeneration column is operating at a low pressure and also high temperature. If let's say the pressure that's going inside this column is at a higher pressure, which means that X6 increases. It means we require higher steam flow to compensate this high pressure in order to allow the CO2 to be stripped off from this solvent. And next, which is the X7, we have the negative correlation, and it is valid because if the inlet temperature of the regeneration column it increases, it means that your reboiler duty will be decreased, and thus the decrease of the reboiler steam flow. Next, I present you the surrogate model for the reboiler steam flow and also the validation for the surrogate model. So from what we can see here is that the red lines will be the model and the blue line will be the actual. And it can be seen that the model is actually following the actual operating trend. And in terms of the R-square, it is validated that the R-square will be around 0.797, which means that this reboiler steam flow MLR model is valid. Moving on next, let us look into the circulation flow performance study, and this is the loading plot of the principal components, and this is the result, and it has the adjusted R-square of 0.881 and with 3 variables only. And the p-value is 0, which is less than 0.05, shows high significance of the variables on the lean solvent circulation, and the VIF, which is less than 5, shows no collinearities in building this model. Similar with the reboiler steam flow, right now we are going to perform the process analysis on the circulation flow as well. Let us look into the first variable. We have the positive coefficient, and it is valid because when your CO2 content increases, it means you require more solvent in order to absorb the CO2 from the natural gas. In terms of the second variable, which is X6, when your treated gas flow increase, it means that you have more feed gas flow, which means you require more lean solvent circulation flow as well. And lastly, we have the S8, and also it has a positive coefficient. We know that our absorber is actually operating under the low temperature and also the high pressure. If let's say your lean solvent temperature has a high temperature, which is opposite to this, it means that we require more lean solvent circulation flow in order to compensate that deficit in order to absorb more CO2. Here I present you the surrogate model for the circulation flow and also the validation for the circulation flow as well. And just by looking at this trend, it is determined that the model is following the actual operation trend. And not only that, the R-square for this validation is 0.8863. It means that with a high adjusted R-square, our model is actually accurate and valid. Moving on next, let us look into the second benchmarking system, which is based on icon steady-state simulation. Right now, let us look into the evaluation of the process efficiency. So here I present you the first unit, which is the absorption unit. So this is the new benchmark for the circulation flow. Unlike the previous benchmarking system, here I considered 4 different CO2 content, which is 3.33 mole percent, 4.5 mole percent, 5.5, and also 6.5 mole percent. So just by looking at this graph, we can conclude that this is a valid benchmark. Why? With 2 reasons. Firstly, in terms of the visual representation, these 4 lines are actually enveloping the current operating. It means that it is valid because it is following the trend. And not only that, in terms of the relationship between the circulation flow and also the production, it is in linear relation, which is accurate. Let us look in terms of the efficiency for this absorber. So in terms of the absorption efficiency, it's determined that the ideal case will be around 75%, and for this absorption unit, which after trial and error, it is determined that the absorption efficiency is approximately 61.9% with a reduction of 13.1%. So by implementing this new benchmark system, what can we conclude? We can actually determine that there will be 36% of the circulation flow per annum savings. And what does this mean? It means that there will be 36% money saving as well. And do you think that's the only advantage? My answer will be no, because there are additional advantages in terms of the pumping cost reduction, because there will be less pumping duty due to the less circulation flow requirement, and also the cooling cost reduction because you require to cool down less solvent and thus less cooling duty. Next, let us look into the second unit, which is the reboiler steam flow. So here I present you the new benchmark system for the reboiler steam flow, and it is similar to the circulation flow, for which the CO2 variations are considered. So after implementing this new benchmark, it is determined and calculated that 130 tons per day can be saved and turned into money saving. Around 1.2 million Rm per year can be saved. How about in terms of the efficiency for this reboiler? Through calculation, it is determined that around reduction of 4% of efficiency of the reboiler only. Right now, let us compare between the before and after the new benchmark. So for the before, which is the current benchmark, CO2 variation are not considered. And for this new simulated benchmark, CO2 variation are considered. And for the current benchmark from company A, the correlation are unjustified. And in terms for this simulated, the correlation linear and it is well justified. So, what can we conclude by far? In terms of this absorber, it is determined that it is operating at a moderate efficiency, which is indicated by the efficiency of 61.9%. In terms of this reboiler, it has a high efficiency as indicated by the 4% drop of the efficiency only. So it can be concluded that the reboiler steam flow is high is due to the low efficiency of our absorber. To conclude my presentation today, I would like to make comparison between the current benchmark system, MRR models, and also the steady-state simulation. So for this current benchmarking system, it is practical but it is inaccurate because it has a wrong boundary set and it does not consider the CO2 variations. In terms of the MRR models, it is practical but it is slightly inaccurate because it is based on the current unjustifiable operations. So for this steady-state simulation, it is rather complex but it is very informative, and it has a new boundary set, and it considers the CO2 variation as well. Of course, it has its own limitation. In terms of the limitation, it only considers the equilibrium condition because it is steady state, and it does not consider transient condition, and the size of the equipment is not considered as well. So to better improve this project, here are some recommendations. So firstly, root cause evaluation of the assets use of the steam on the circulation flow, and followed by the development of the multiple benchmarks to tackle different operational conditions. And thirdly, dynamic simulation is highly recommended. And lastly, the incorporation of the process control into the energy optimizer is highly encouraged as well. Here I end my presentation. Thank you.